Hi everybody, it's Mr. Molikash. I'm back for another fun-filled week of Calculus 1, and if you haven't noticed, calculus is getting tough. It is getting tough. I'm going to try to encourage you the best I can. I know it's really difficult right now, and to be honest, the only way that you can be good at calculus problems is to do lots of practice. So my videos are meant as an introduction, first point of contact when you're learning something for the first time in calculus. There are tons of videos on YouTube. There are tons of resources out there that are free that you can use to get really good. And your textbook, if you're one of my students, your textbook is one of them. I'm using my own textbook here for the purpose of these videos, but your textbook is just as good as this one. There's lots of free resources out there. So I want to encourage you, if you're watching this, that after you get done with my instruction, watch it a couple of times, but then you just need to get lots of practice to be good at this. So there's going to be two things that we're going to do this week. We're going to start evaluating integrals of more difficult functions. We're going to do something called U-Substitution. And then we're going to do one that's a little bit more difficult. We're going to do U and V substitution. So to start with, let's just jump right in and do U substitution. And I think this is a little bit too big. Okay. So the idea of U substitution actually traces itself back to the chain rule. So over here I'm talking about the chain rule. And, you know, for the function, like, let's say that you had y equals the sine of x, right? So you know that the derivative, dy dx, is cosine of x. Easy peasy, lemon squeezy, right? But if this was something more difficult than x, more complex, I guess, not necessarily difficult, you know, let's say that we put something inside of the sine function like x squared. Then what we have to do the derivative is, remember, we have to attach the derivative of the inside, right? And we learned that earlier a couple of videos ago with our derivative techniques, right? So if this is the derivative of this, then it must be the case that if we were to integrate this big thing, and I'll put the 2x in front, 2x times the cosine of x squared with respect to x, then that would be the reverse derivative called the antiderivative. Remember, this is an indefinite integral, right? So indefinite integrals have to have the arbitrary constant on the end, the general antiderivative. So the idea of U-substitution, what it does is it allows you to figure this out, this reverse derivative techniques, kind of like undoing the chain rule. And the people that are really good at this, the people that are really good at finding out how to do this, know how to decompose functions. So let's talk a little bit about, before we do the integrals, let's just talk about algebra for a minute, right? Let's say that h of x is the sine of x squared. Okay, well, that means that there's an outer function f of x, which is just the sine of x, and then there's an inner function g of x, x squared, so that h of x is f composed of g of x, right? So if I were to put this in the place of x, I would get my h function. And you have to be really good at seeing that. You have to be good at seeing, like, what is the inside function, the innermost layer of the onion, if you will. And it's possible to have several layers. You could have f of g of h, or you can have, you know, several different nestings of these compositions of functions. Okay, so let's just say that we were to start from scratch, right? Let's just start from scratch, and let's figure out how would we do the integral of 2x times the cosine of x squared. So when I'm looking at this, And I've been, doing these for many years, so I know what to look for, and I'm going to tell you what to look for. Look for the more complicated function, the x squared. Okay, and you notice that the derivative of x squared is out here, right? So what you do in U-substitution is you call that function by the variable u. You say u is equal to x squared. So when we rewrite this all over again, we say the cosine of u. Okay, so that's step number one, is to identify like the innermost function inside the other function. And our hope is that the derivative of this innermost function is also up there, and so that the chain rule has already been done for us. Now the goal from this point on is to make sure that 2x is also, that there are no x's in the integral. We're going to change all the x's to u's. So the dx will eventually turn into du, and the 2x may disappear altogether. I'll explain why. So the integral sign stays the integral sign. So let's figure out, like, what we have to do is differentiate this, both sides, with respect to x, right? So if you differentiate this, you get du dx equals 2x, which we've already mentioned, right? But what's customary in integrals is not to write it like this. What we do instead is we write du by itself. We write what's called the differential form, for you ultra math geeks out there, du, and we take the dx and multiply it by the 2x. So we say du is 2x dx. Okay? Alright, so what I'm going to do, especially since you're learning this for the first time, most of you that are watching this, I'm going to highlight what I haven't substituted yet. I've already got my cosine. I already know that x squared is something that I called u. And I got to figure out what the rest of this is. What's this 2x times this dx? Well, it just so happens, let me make my highlighter a little bit bigger. It just so happens that what I have left over is exactly du, right? So I'm now going to substitute with the right pen. I'm going to substitute this times this and make it du. Okay, now this black problem is much easier to do than the pink one is. So we traded a hard integral for an easier one by replacing this complicated function with just one variable u. And again, our hope is that everything else that's out there is the derivative of what the inside was. So this is the chain rule essentially that's already been done, right? The cosine of u times the derivative of u. And the integral of cosine, of course, is the opposite of sine. Is that true? Nope, that's not true. The derivative of cosine is the opposite of sine, right? So don't make that mistake, okay? Don't make that mistake. You want to know that the antiderivative is the thing whose derivative is cosine, and that's the sine of u. What am I supposed to tack on to the end of this since there's no numbers on my integral? You're right, plus c. Good. Now, the original problem was written in pink with the variable x. Currently, I have an answer using the variable u. So what I have to do is back substitute. I am now going to change the u back into x squared. So the final answer is the sine of x squared plus c. Okay? So that is a step-by-step rundown of why the antiderivative of this big huge thing is equal to this. And again, you can check your answer by finding the derivative of this, right? If you find the derivative of this, you should get cosine of x squared times 2x, right? So this is kind of like the reverse chain rule. That's what the U-substitution is, okay? Now, you might have a problem where like the derivative of x squared doesn't exactly match. It's not automatically there, right? So we're now going to do a problem where we have to kind of make it fit. We have to make it fit. And that's this one I'm going to do right here, number 3. So let's do this one. The integral of x times the cosine of x squared minus 1 dx. So I'm going to ask you, no pun intended, I'm going to ask you to decide what part of this integral I should let u equal. If you were listening just now, maybe you know that. Okay, so if you guessed x squared minus 1, that is correct. X squared minus 1. Now you might be like scratching your head right now because you think, okay, if you're working ahead, you know the derivative of x squared minus 1 is 2x, and there's no 2x here. Never fear, we're going to make it fit. We're going to work it out. It'll be okay. So let's proceed with our steps. I'm going to find the derivative of u, which is 2x. Remember, this is du dx equals 2x, so my dx I'm going to write over here. Okay. And I'm going to substitute, right? So let's see what I've got first. I've got the cosine of u, and then I have x dx. So what is x dx? Well, x dx is right here, isn't it? Right? X dx is right there. So what I have to do is I have to replace the x dx with some expression in terms of u. That's over the variable u. So I want to solve this equation for x dx. I want to get x dx, these two things, I want to get that by itself in the equation. How do I get that by itself? I just divide by 2, right? So I can multiply both sides of this by 1/2, right? And then this cancels out. So now I know that x dx is exactly equal to 1/2 du. Not a problem, because remember, with constant multiple, we can take that outside the integral, right? So this is the same thing as 1/2 times the integral of cosine u, which we just did a few minutes ago. That is going to be sine u plus c. And 1/2 times c is just another c, right? From c to shining c. Arbitrary constant. 500 times c is another c. And we have to back substitute, right? So the final answer should be 1/2 times the sine of what? What did we originally say that u was equal to? It was x squared minus 1. Okay, so this is the way to do an integral using U-substitution. Now I want to rewind a little bit just in case this business of multiplying 1/2 confused you. Okay, there's another way to think about this. So let me go back to that part of the video for a moment and try to erase my black stuff here. So let me go back to that and ask you to possibly consider something else if that was confusing. Okay? And the something else that I want to do is this. I want this du to be in the integral, right? So in order to make the dx into du, I want a 2 to be here. See this 2? It's not there, it wasn't there, didn't work out, right? So you know what I'm going to do? I'm going to put a 2 there. I'm going to put a 2 there so that I can have what I need, right? By putting the 2 there, I also need to multiply by 1/2 to compensate for that, because 1/2 times 2 is 1, and then all the pink stuff stays unchanged, right? So now I have my 1/2, but all of this 2x times dx is exactly du. See how that works out? So maybe that's a little easier for you to think about to get the answer. So now we have, the antiderivative and blah, 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 back substitute. Maybe that's a little bit of an easier way of thinking about that. I've taught it both ways, and some students like the first way, some students like the second. So that's kind of how that works out. All right, we're going to do another example now of U-substitution, and then we'll try to start talking about integration by parts, which is, I would say, I would possibly like watch the other part, like the integration by parts, on a different day after you've gotten good at U substitution. Now we'll talk about that in a moment. But let's see, what is the integral of the tangent of x? So we know the integral of sine of x, that's the opposite of cosine. We know that, plus c. We know the integral of cosine of x. We've been doing it a lot here recently. How do we do the integral of tangent of x? Well, one trick that you can do is rewrite it in terms of sines and cosines. So we all know that by the time you're getting into calculus, you know that sine divided by cosine is exactly equal to tangent, right? And the trick for this one is to let u be the bottom of this fraction. And the derivative of that is negative sine x. The dx gets moved over, okay? And just like the technique that I showed you earlier, we want the negative sign to be in this integral, right? So we put one there and we put one out here to compensate for it, right? All right, so all of this stuff is du, right? All that pink stuff is du. There's a negative sign outside this integral because I had to multiply two negatives to make sure the black stuff was unchanged. So what's left over? What's left over? What's left over is a u on the bottom and a 1 on the top. It's 1 over cosine of x, which is 1 over u. And by now we know that the integral of 1 over u is the natural log of the absolute value of u. So what is the integral of tangent? It's the negative of the natural log of the cosine of x plus c. And if you don't believe me, find the derivative of this function. It will be exactly sine over cosine, positive sine over positive cosine, which is exactly tangent. Okay, so this is, again, I want to repeat my video right now is telling you some introductory information about U-substitution. You need to work lots of problems. You need to see lots of examples, and you'll be training your mind of like how to find U. Not how to find yourself. How to find the function that you're going to let U equal. Okay, so again, just reiterating the steps, you have to let part of your function equal U. You're hoping that the rest of your function is the derivative of u, and then you have an easier integral that you can find the antiderivative of, and then finalmente, for you Spanish-speaking folks, finally, you always have to back substitute. Do not leave u in your answer. Leave x in your answer. Okay. All right, so now we're going to move on to, and there's more examples in my book. There's more examples all over the internet. I would encourage you to possibly watch Khan Academy or Patrick JMT. There's tons of calculus videos at Patrick JMT. Patrick, if you're watching this, I'm promoting you, so hope you don't mind. All right, so now we're going to do some integration by parts. So let me come over here and go to the integration by parts, which is in the advanced integration techniques. Okay, so integration by parts, if you've been looking at this video for any length of time, uses two variables to substitute, and I want to explain that in great detail. But I also want to warn you, if you've gotten to this part of the video, you need to make sure that you're really good at U-substitution before you proceed. So go back and get some practice in your textbook, watch more examples, work out more problems, get good at U-substitution. Okay, now having said that, I'm assuming that you know how to do U-substitution very well. So let's remember what the product rule of two functions is, right? So if y is equal to two functions, u times v, where u is a function of x and v is another function of x, and they're multiplied, right? So something times something. okay? dy dx is the derivative of u times v plus u times the derivative of v. Okay? Now, because of differential forms, there's some mysterious math going on in what I'm about to do, but I'm going to multiply both sides by dx. And there's some very deep mathematics that goes on in what I'm doing right here, okay? If you go into the theory of calculus and you go take some calculus courses in graduate school, you know I'm not really multiplying by a number, okay? I'm multiplying by a very small differential. So anyway, having said that, I'm going to do some what mathematicians would call hand waving. All right, so the dx's cancel, and I get v times du. Oh, let me write this backwards to fit what I know as a formula. Okay, so u times dv plus v times du. And I'm writing it like this for convenience. I just like the u coming first. So u dv plus v du, right? So essentially this is the product rule, right? All this is the product rule for derivatives. All right, now we're going to undo that. So we're going to integrate both sides. We're going to integrate this, and we're going to integrate this. We're going to integrate both of them with respect to x, and that essentially is what cancels out the dx's. If you want to go do some research, like if I integrate both sides with respect to x, that's kind of what cancels out the d. All right, so the integral of dy is y, right? And I have to integrate both sides of this, right? So the trick in integration by parts, okay, the trick in integration by parts is to know that your original function, which is uv, right, this is y, which remember was uv, is the sum of two integrals, u times dv plus the integral of v times du. But remember, in the beginning, y was uv, right? So essentially the derivative of this is what's behind the integral signs, right? So if we integrate both sides, we get the original thing. That was the product. All right. What integration by parts, the integration by parts formula is exactly this, just rearranged a little bit, okay? So you are going to have an integral that looks like this. It's going to have a u in it, and it's going to have a dv. We have to pick which part of our integral is u and which part of our integral is dv. I'll show you that in a minute. But if I solve this, I have to do the integral of v du subtracted from uv, right? So this is uv minus the integral of v du. Okay, now if you're taking good notes, and if you're one of my students, I really hope you are, this is the formula for integration by parts. Now let me tell you why it's called integration by parts. Because there's going to be two parts to our integrand. There's going to be a part that we have to differentiate. We have to find du. And there's going to be another part that we have to anti-differentiate. And what this does is, the purpose in integration by parts is to trade a hard integral for an easier one. Okay, I haven't put a smiley face on that yet because this requires that you're good at U-Substitution, right? So it depends on how good you are at U-Substitution. This may not be an easy integral, but it is easier than the one that you started with. Okay? So integration by parts is not for the faint of heart. This is difficult, especially at first. So hang in there as I show you an example. Okay? So now that we've got that formula, let me write that at the top. Okay? The integral of, whoop, I messed up. It happened again. I tried really hard not to make that happen. I pressed the button, y'all. My bad. Pressed the wrong button. So anyway, the integral of u dv is equal to uv minus the integral of v du. I'm trying to make my v's pointed so that they don't look like u's. Okay. So this is the integration by parts formula, right? And let's say that we have, I don't know, I'll give you an example to start with. So this one down here. Let's solve this integral. The integral of x times e to the x dx. Okay. So I'm going to do this problem, and I'm going to explain the whole LIATE, I guess, strategy for picking which part is u. And I mean the variable u from before. Okay, so here we go. I'm going to let u, the u part, be x. I'll explain why in a moment. But just know that I'm going to let u equal x. That means that the other part of the integral, e to the x dx, is going to be dv. So the dv is e to the x dx. So I have part of my integral that's a u and part of the integral that's a dv. And it's very important that you make the right decision as to which part is which. That's where all this comes in, and we'll talk about that in a few minutes. So what do I have to do here? Well, I am going to have to figure out what du is, because there's a du in the formula. And I'm also going to have to figure out what v is, because there's a v in the formula. How do I get from u to du? Find the derivative. The derivative of x is 1, but this is du dx equals 1, so I'm moving my dx over, so du is going to be exactly dx. V, on the other hand, is going to be the antiderivative of e to the x. So if I integrate both sides of this little differential equation, the integral of dv is v, the integral of e to the x dx is e to the x. Technically, there's supposed to be a plus c here, but I'm going to bag that plus c and wait until the end to write it down. You'll see what I mean in a minute. Okay? So, now what I'm going to write out for the answer is u times v. So I have to do this times this. So let me write out the answer. It's uv minus the integral of v times du. So what was u? It was x. What was v? It was e to the x minus the integral of v, which is e to the x, times du, which is dx. Now I'm hoping that at this point you can see why I said what I said earlier. This harder integral has now been traded out for an easier one. The integral of e to the x is super easy, right? Okay, so the integral of u dv is exactly the problem that we have. We chose the right part for u and the right part for dv, the right part for u, literally, pun intended. Okay, enough math jokes. The integral of e to the x is just e to the x. And remember that plus c I forgot to write down earlier? Yeah? I'm going to write it down now. So here you go. This is exactly the integral value, the indefinite integral of x e to the x dx. And if you don't believe me, find the derivative of this. Pause the video and go differentiate this. The derivative of c will be 0. You'll have to use the product rule here and then subtract e to the x, the derivative of e to the x is e to the x, from that product rule, and you'll find out what happens. It'll work out. Okay? Now, let me go talk about how I made the choice. This is probably the most important part of this video, okay? How did I know that this was supposed to be U and this was supposed to be dV? Well, there's a guideline, there's a strategy you can use, and the main goal in integration by parts is to let U be the part of the integrand whose derivative is simpler than U. So the derivative of x is simpler than x, it's just 1. It gets easier, right? We want this side to become easier. Then we want the most complicated part of that integral that we can do an antiderivative of. And maybe that requires U-substitution, right? We might have to do a U-substitution issue here, right? Okay. So there is another way to determine this part of the integrand should be U, and it's the acronym LIATE, L-I-A-T-E. Sounds like an Italian word. LIATE, right? So L-I-A-T-E. All right, so what does that all stand for? If you've been reading over here, maybe you know if you've read my book. Okay. L stands for logarithms. I stands for inverse, and specifically inverse trig. Those are difficult functions to work with, but like inverse sine, inverse cosine, inverse tangent, inverse secant, even. A stands for algebraic. What is an algebraic function? A polynomial, a square root function, a rational function. 1 over x, square root of x, x to the 3/5, x squared plus 2x plus 1. Those are algebraic functions. T stands for trig. E stands for exponential. So between my algebraic function and my exponential function, I picked that one first. So this was my U, which means that the exponential part was the dV. Okay? And 99.9% of the time this works out. Okay? If you're one of my students, you'll never see a problem where this doesn't work. Okay? There are problems out there. Somebody's watching this video knows what I'm talking about, where that doesn't work out, and they're very, very weird cases. Okay? So here's another one. Let's just integrate the natural log. And I screwed up again. Sorry about that. Keep hitting this button by accident. All right, how do we do the natural log as an integral? Now, first of all, the answer to this is not 1 over x plus c. That's bad. Don't do that. Okay? That is definitely not the answer. In fact, if you wrote this, you're finding the derivative of the natural log, right? So it's definitely not 1 over x. But keep that derivative in your back pocket for a moment, okay? Remember that logs are first on the list for u, right? So I'm going to let u be the natural log of x. So what does that leave for dv? It leaves dx. So let me do some highlighting so you can see what I'm doing. This part is going to be u, because logs are always first on the list for choosing u, making the right choice for u. So that means everything else in the problem is dv. Okay? By the way, I should write my little formula up top here, so let me do that real quick. That's way too big. All right. So the integral of u dv is equal to uv minus the integral of v du. There we go. Now I'm going to allow you to pause this video, and I want you to do two things for me. I want you to find the derivative of the yellow part in differential form, and the pink part I want you to find the antiderivative of. What happens when you integrate dx? Okay, so you've unpaused the video. You should have gotten 1 over x dx. Remember that thing I told you to have in your back pocket? Now, this is not the answer to the entire integral, but it's going to be part of the thing that we use to get the answer. Okay, stay with me. So dv is dx. What is v? X. Right? The integral of 1 dx is just x. So how do we put all this together? We have to do uv, let's write out the formula, minus the integral of v times du. Now here's why this almost all the time works. Okay, here's why this works. We're going to do u times v, which is x times the natural log of x, and for some reason my pen doesn't want to work over there. Sometimes this pen software doesn't really want to work out. So, you know what I'm going to do? I'm just going to wait. Okay, it appears as if everything is working now. We'll see if my memory has caught up with me. So uv, which is x times the natural log of x. Now, you might have been thinking, yeah, you're supposed to do natural log of x and then times x. But if I do natural log of x, it's kind of like the natural log of x squared, so I want to put the x in the front. Alright, that's the reason I did that. Minus the integral of what? V times du. Well, v was x, and du is 1 over x dx. Look what happens. Ta-da! This is a very easy integral. We've traded a hard integral for a super easy one. Super easy one, right? So the answer to this is x times the natural log of x minus, what's the integral of 1? X. What do we have to tack on the end? Plus c. The end. Okay? So I explain all that here in my book. Okay? I also do some harder examples here if you want to look through them. There's even something, and if you're really up for a challenge, you want to search Patrick JMT's videos for what's called a loopy example. I don't have time to go through that in my video, but search the loopy example on Patrick JMT in YouTube, and you'll see what I mean. That's what happens when you have a trig times an exponential. They're the last two on the list. There is a trick to do this, and it requires that you do integration by parts twice. So the easier integral is another integration by parts problem, and it loops back to the original when you kind of take advantage of that fact. But somebody out there knows what I'm talking about, but not for this video. Okay? Alright. So the goal in integration by parts, okay? First, you have to know that your original problem or integral is the integral of u times dv. Okay? You have to use a guideline to figure out which part of this is u. Whoops, I messed that up. I meant to highlight. Which part of your integral is u? Okay? You also need to know which part of your integral is dv. The u part is either a log, an inverse trig, an algebraic, a trig, or an exponential. In that order. Okay? Once you find u, you know what u is, you know what dv is. You need to find the derivative of u, and you need to find the v, so that when you write your answer out, the answer to this is u times v minus the integral times vt du. So you multiply those two together and subtract, very important that you subtract the integral of v times du. And our hope is that this integral is easier. It may not be easy, but it's easier than the original one was. So there you have it. That is the reason for integration by parts. Leave me a comment if you would like some help on this, if you want more examples, if you want a copy of my book, leave me a comment and I'll send you a copy of the book for free. It's 300 pages, but I don't care. I'm not going to print it for you. I'm going to send you a PDF. Okay, I mean, we're talking free here, right? And I know it sounds cheesy, but like and subscribe, because I have an entire playlist of Calculus 1 videos starting from the very beginning of Calculus 1, and my plan is to go all the way to the end to do all the integrals, differential equations, and such. So it's been a joy and a pleasure to do these videos. I want to encourage you to hang in there. Calculus is hard, but you got this. Hang in there and get the practice you need. See you next week.